The lessons in this physics unit tend to build off of one another. So the first lesson we talked about speed, and then we kind of added to that. We looked at velocity, right? It's a vector. We talked about distance versus displacement, and then we went to acceleration. So today what we're going to do is build on those lessons as well, and we're going to learn a couple of new formulas and a few different concepts. So today we're going to talk about force, work, and energy. And before we get into the math of this stuff, let's define what these things are. So a force can be defined as a push or a pull on an object. Okay, so a force is any push or pull on an object. Now, Sir Isaac Newton, you may be familiar with his name. He's kind of associated with gravity. There's a famous story where he was sitting under an apple tree and he was kind of contemplating the universe, and an apple fell down and hit him on the head, and that kind of led him to talk about the law of universal gravity. But he's also known for his laws of motion. So there's three of them. An object at rest tends to stay at rest. Okay, an object in motion tends to stay in motion. Right? And for every action, there's an opposite and equal reaction. So those are his laws of motion. Now, an object will stay at rest unless a push or a pull or force is applied to it. An object will stay in motion and continue down that track in that direction unless a push or a pull, okay, a force is applied. So we can mathematically calculate these pushes and pulls, these forces, using the formula F equals ma. So you'll notice that there are arrows over the F and the A, and those arrows signify that these things are vectors. Okay, so what that means is there's a direction. Now, the reason why I brought up Sir Isaac Newton is because the units for force are actually named after him. So the units for force are calculated in newtons. Now, this is kind of a made-up unit, and a newton actually stands for a kilogram meters per second squared. So what that means is when we're calculating force, our mass is in kilograms. Now this is important because sometimes you might get a question where I give you the grams, right? How do we go from grams to kilograms? How do we convert grams to kilograms? We divide by 1,000. Okay, so if we divide the grams by 1,000, this will give us our kilograms. Now, acceleration, we know the unit for acceleration is meters per second squared. So if we multiply these two things together, we get a kilogram times meters per second squared. But this is hard to write out every single time, so we just call this a newton, okay, in honor of Sir Isaac Newton. So remember, acceleration is a vector, so it has a direction. Therefore, force is also a vector. So let's take a look at a typical question where we have to calculate force. So hopefully by now, we've done speed calculations, we've done velocity calculations, we've done acceleration calculations. They're all done the same way, right? Number one, write down your variables. So an athlete throws a 12 kilogram shot put. Okay, that's our mass. Mass is equal to 12.0 kilograms. Okay, and it accelerates from her hand at 2.0 meters per second squared. So that's our acceleration. How much force did she apply to the shot put when she threw it? So what we're looking at is force. Okay, so remember, you guys, you get a point for writing down your variables. You get a point for putting down your formula and then manipulating it if we have to, but the formula is okay the way that it stands right here, so we just substitute in our values. 12.0 kilograms is the mass. The acceleration is 2.0 meters per second squared. So the force that she applied to that shot put would be 24 kilograms times meters per second squared. Now, we will change this into a more simple unit, so the answer would be 24 newtons. Now, I said that force is a vector, but I don't have a direction here, or do I? Well, yes, I do, because it's positive, all right? So positive is direction, remember? Okay, so the force that was applied to that shot put was 24 newtons. So I would get a mark for my variables, I'd get a mark for my formula, I would get a mark for my answer with the correct sig digs and the correct units. Okay, 2 significant digits because 2.0 has 2 sig digs. Okay, let's do one more example here. A soccer player kicks a 450-gram soccer ball with 20 newtons of force. How fast will it accelerate off of his foot? Okay, so again, you guys get into the habit of this every single time. Write down your variables. So we have a mass. Mass is equal to 450 grams. But remember, you guys, when we're dealing with force, mass has to be in kilograms. How do I find kilograms? Divide by 1,000, and I get a mass of 0.450 kilograms. Now here, the force is positive 20 newtons. Okay, so it's a positive. I don't have to write positive, right? We know that by default it's positive, so that's the direction in this case. And what we want to know is how fast does this accelerate off the soccer player's foot? Okay, so force is equal to mass times acceleration. All right, I obviously have to change my formula here because I need to find acceleration. So how am I going to get rid of mass? I do the opposite operation. So if I'm multiplying by mass, I divide, get rid of the m. What I do on one side, I have to do to the other. So acceleration is equal to force divided by mass. Okay, the force is 20 newtons. The mass is 0.450 kilograms. Now, remember, ladies and gentlemen, a newton is also, if I just write it the other way, a newton is a kilogram times meters per second squared, right? So look at the formula. Kilograms is going to cross off. What am I going to be left with? Meters per second squared, which is acceleration. Okay, so I know I'm on the right track here. 20 newtons divided by 0.450 kilograms gives me an acceleration of 44 meters per second squared. Now, it's a positive, so I don't have to put any direction. Just having a positive gives me my direction here. Okay, and I check for my units and I check for my significant digits. All right, so I would get 3 out of 3 on this question. So as I mentioned before, Newton came up with these laws of motion, and one of the laws of motion was an object will stay at rest, okay, unless a force is applied to it. An object will stay in motion and it'll go in a certain direction unless an opposite force is applied to it, or an unbalanced force. So an unbalanced force is a force acting in a direction that's greater than the force acting in the opposite direction. Okay, and when you apply an unbalanced force to an object, you will cause it to either change direction or speed. Now, building on this idea of force, we have another concept called work. Okay, and in physics, work is different than in real life, right? We often say, well, I have to go to work, or I'm working today, okay, or oh, well, that was a lot of work. But in physics, work is a very specific thing. Okay, work is defined as the energy transferred to an object when a force is applied to that object. Now, here's the difference between physics work and everyday work. Okay, in physics work, it's a force applied to an object, and the object has to move. All right, so there has to be movement in order for work to be done to an object. All right, so in physics, in order to do work to something, 3 conditions have to be met. Number 1, there has to be a push or a pull applied to the object. Now, this push or pull could come from you, or it could come from the earth, right? The earth pulls things down. We talked about that, right? The earth has a force to it. The gravitational force applied to objects will pull objects down toward the earth. Okay, so there has to be a push or a pull. The second condition is there must be movement. So again, this kind of illustrates the difference between how we talk about certain things in a physics context and how we talk about things in the real world. If you've ever done a plank, you're doing work, right? It takes a lot of energy. You know, you hold that plank and you start to shake, and for sure you're doing work, aren't you? Well, not in a physics context, okay? In order to do work in physics, there has to be movement. So a plank is, in physics, you're not doing work, okay? But a push-up, you're applying a force, a push, and you're moving. So this would be work, this would not be work in a physics context. Okay, in the real world, obviously, if you've ever done a plank, you know you're doing work, but that's not the physics definition of work. And then lastly, the direction of the force and the direction of the movement must be the same. So if I'm pushing to the north, if I'm pushing a box to the north, and the box moves to the north, then I'm doing work to it, okay? The force is in the same direction as the movement. Now, work is measured in another kind of made-up unit called a joule, and that's named after a scientist as well. Now, the unit joule is also the unit for energy, but remember, work is the transfer of energy to an object. So work and energy are related to each other. So work is the transfer of energy from one object to another, or from one form to another. So again, there is a formula for calculating the amount of work that's being done to an object. And the formula is W, okay, work is equal to F times D. Now, F is force, okay, again, I'm not too picky with the vector symbol over acceleration and force because we know those are vectors. And then distance, okay, distance is measured in meters, force is measured in newtons, and work or energy is measured in joules. Now, work and energy are scalar quantities, so we don't have to worry about direction when we're talking about work. So let's try some examples here. Practice example number 1. A tugboat is towing a tanker through a canal using a tow rope. Calculate the work done by the tugboat if it applies an average horizontal force of 6.50 times 10 to the 3 newtons. Okay, the tanker moves a horizontal distance. So this is important, you guys, because a horizontal force was applied and the tanker moves in the same direction as the force. So work is being done here. All right, so let's put down our variables. We are looking for work, okay? They give us the force, force is equal to 6.50 times 10 to the 3 newtons. Okay, and what they're asking us for is the work, so they have to give us another variable, which in this case is distance, and they're telling us that the distance traveled by the tanker is 150 meters. So is work being done? Is this meeting all the criteria of work? Is the force being applied to the tanker the same direction that the tanker is moving? It's horizontal. Yes, the tanker is moving, so work is being done. So we write down our formula. Work is equal to force times distance. Work is equal to 6.50 times 10 to the 3rd newtons times 150 meters. Okay, the amount of work being done to this tanker by the tugboat is 975,000 joules. Now, I can't leave it like this, right? That's the wrong amount of significant digits. How many significant digits should my answer have? Well, distance has 3 sig digs, force has 3 sig digs. Remember, we don't count this in our significant digits, so my answer has to have 3. Can I just round my way out of this problem? No. So how am I going to put this into 3 sig digs? Scientific notation. So work is equal to, I'm going to move this 1, 2, 3, 4, 5 decimal places to the left, 9.75, I get rid of all these zeros now, times 10 to the 5th joules. Okay, our next example, a large crane did 2.2 times 10 to the 4th joules of work in lifting a demolition ball a vertical distance of 9.5 meters. Okay, so there is movement here. The ball is raised above the ground. Okay, so what we want to do here is calculate the average force that's exerted on the ball by the chain. Okay, so again, you guys, you should be getting the hang of this. We're writing down our variables. So in this case, they tell us that work is being done. 2.2 times 10 to the 4th joules of work. The distance traveled by this demolition ball is 9.5 meters. And we want to know what the force is. So work is equal to force times distance. Obviously, we have to rearrange our formula. We have to get rid of distance on this side of the formula. So I'm going to divide by distance here. What I do on one side, I have to do to the other. So force is equal to work divided by distance. Work is equal to 2.2 times 10 to the 4th joules divided by 9.5 meters. And the average force applied is equal to 2,315.789 newtons. Okay, so obviously I have to go back and check my significant digits. How many sig digs should my answer have? Well, there's 2 in work, right? And there's 2 in distance, so my answer has to have 2 significant digits. So in order to do that, first I'm going to move my decimal place 1, 2, 3 places to the left, and then I'm going to round to 2 significant digits. So what I want to do is just have it to 1 decimal place. So I'm going to round the 3. Do I have to round the 3? Do I have to change it? No. So this just becomes 2.3 times 10 to the 1, 2, 3. And what's the unit for force? Newtons. Okay, Example number 3. A large crane did 2.2 times 10 to the 4th joules of work in lifting an object. How much energy did the object gain? Well, remember you guys, this is a bit of a trick question, okay? Remember you guys, work is the transfer of energy through a push or a pull, okay? So this crane is lifting an object. It's pulling the object upwards, okay? And it's doing 2.2 times 10 to the 4th joules of work in order to do that. Now, once this object gets lifted above the ground, how much energy does it have stored in it? Well, the amount of energy, okay, E is energy, is equal to the amount of work that's being done to it. So this is actually a pretty easy question. There's no calculations involved. So how much energy did this object gain? It's exactly equal to the amount of work that was done to it. So the amount of work that was done to this object is 2.2 times 10 to the 4th joules, which means how much energy does that object now have stored in it because of gravity, because it's above the ground? 2.2 times 10 to the 4th joules. Okay, so work is just the transfer of energy. Okay, so the amount of work you do to something is the amount of energy you've put into it. Now, the last example here, you guys, is a little bit more complicated. Okay, it involves an extra step here. So let's take a look. We're still going to do it exactly the same way, though. Okay, so Mr. Forestier is out with his friends. Yes, I actually have friends. I know it's hard to believe. When his truck runs out of gas, the truck has a mass of 1,250 kilograms, 1,250 kilograms. Okay, the truck starts at rest. It stopped, and me and my friends, we push it. Okay, we apply a force to it, and it accelerates to 2.3 meters per second squared. The truck moves 218 meters to the nearest gas station. Determine the work done on the truck. Okay, so I know there's a lot going on here, you guys, but we do it the same way, right? If you're confused, and this is a kind of a confusing question, always start by listing your variables. So what variables do we have? We have a mass. Okay, the mass is 1,250 kilograms. Now, I'm going to be dealing with work. Work has force in it. Force, when we talk about the mass in force, what's the mass? The units for mass? Kilograms. So I'm good here. I don't have to change anything. Okay? Now there's an acceleration of 2.3 meters per second squared. And there's a distance of 218 meters that the truck travels. We want to know what is the work being done by Mr. Forestier and his friends. Okay, here's the thing, you guys, right? So the formula for work is W equals force times distance. Okay? Now, some people would kind of get confused here because if I look at my variables, I have a distance, great, but I don't have a force, right? So people might think, well, I can't answer this question. Here's where the extra step comes in, you guys. Is there a way to actually find force? If I wasn't given force in the formula, is there a way to find it? Remember, force is equal to the mass times the acceleration. Now, do I have both mass and acceleration here? Yes. So force is equal to 1,250 kilograms times 2.3 meters per second squared. Okay, so I can actually calculate the force being done to the truck. Okay, and the force is equal to 2,875 newtons. Now, when you're doing multi-step questions like this, don't round this answer. Okay, keep it as is, keep it in your calculator. Okay, don't round it. We're going to use this in another calculation, so we don't need to round this as of yet. So now all of a sudden I have found the force, 2,875 newtons. And now I can put this into my work formula. Okay, so the force that was applied to the truck, 2,875 newtons. And the distance that it traveled was 218 meters. So the work done by Mr. Forestier and his friends to the truck was lots of work was done. So 626,750 joules. Okay, so my answer has to be to two significant digits. In this case, what I'm going to do is I am going to move my decimal place 1, 2, 3, 4, 5 places to the left. I want to keep two significant digits, so I'm going to round my 2 to 3, and I'm going to write this as 6.3 times 10 to the 5th joules. All right, so there's a little bit of extra work that has to be done here, so this would not be out of 3, this would actually be out of 4.